everyone. Thanks for being here, and thank you so much for the invitation and for putting together this workshop, Robert. I will be talking about random unitaries in extremely low depth. What we do is literally in the title. We construct certain types of random unitaries that you can construct with circuits of very low depth. The paper is sort of oldish now, at least over a year, so I assume that some of you maybe have seen the talk or have seen the paper. If that is the case, I hope you will only be bored like 80% of the time, because I have some updates and recent developments in the last fifth of the talk, I would say. Okay, so I feel like most of you might not need motivation for quantum information theory and quantum technologies, but there has been a sort of revolution in the control over quantum many-body systems. And this sort of these emerging quantum technologies lead to the need of getting better and better characterization and benchmarking methods. And one of these methods, for example, is called randomized benchmarking, where you basically apply a sequence of random unitaries to your system, and then you use concentration properties of these random unitaries to check how well you actually did in your implementation. And it turns out that randomized benchmarking is only one of very many cases where random unitaries show up in quantum information theory. In fact, they are sort of ubiquitous, because they can not only be used as a tool to characterize and to learn quantum systems. In fact, I will show you at least one example of such an application. They also show up as part of the probabilistic method. So on one hand, they are sort of a part of designing new protocols and algorithms in quantum information theory, and on the other hand, they are very frequently used as a part of a proof technique, where you, for example, want to show the existence of something, and then you can show that it's true, or this object that you want to show exists with high probability over a random unitary or random state. So these things are super ubiquitous, and the most natural ensemble that you can consider is the most uniform ensemble. So this is the same thing that you would do if you have like 15 balls in like an urn. You know, the most natural probability distribution is the one where you draw each ball with the same probability. And the problem is precisely the concentration properties. And the concentration properties lead to the fact that if you just draw like a small ball, you know, with some probability, this probability will be like doubly exponentially small. And that means to even cover like a tiny fraction of all of the unitaries, you need many of them. In particular, you need exponentially many, doubly exponentially many. And that leads to this sort of simple counting argument that already shows up in classical computer science, where you do the same thing with Boolean functions, shows that most of these uniformly random unitaries require exponentially deep circuits. So that means they will A, never show up in nature, and B, we can't build them. So first of all, for the first application where we try to use random unitaries in protocols, that sucks because we can't build these things. And the second one, where we use them as part of the probabilistic method, now we get the existence of some objects, but they will be some, you know, highly complicated objects that we will actually never see in practice. So ideally, we would like to have some technique that gives us the existence of some object that we could even build, or that might actually show up in nature. And the idea is now, and it's an old idea, to replace these uniformly random unitaries by something that only looks like a random unitary in some experiment. And the idea is that you can have an observer that could, for example, do some quantum experiment. These unitaries, you know, they are quantum operations, so you can apply them to some state. And you can set up a quantum experiment, for example, adaptively in such a way. You know, you first have some initial state that you picked. You black box apply your random unitary. You know, if you push a button and then the random unitary is applied, and then you do some measurement setup, for example, or some unitary evolution. Then you perform another black box random unitary, and so on and so on. You do some measurements. And in this setup, you could ask the question, is it possible for the observer to tell the difference between something that is not actually uniformly random and something that is? And there are two ways to define objects that are indistinguishable in sort of these restricted settings. And both are interesting for some reasons. The first one is called unitary designs, and basically says if this observer only has access to k copies, then it's perfectly impossible for this observer to tell the difference between a uniformly random unitary and maybe something that was drawn from, for example, random quantum circuits or something where we can pick the depth of the circuit that generates the random unitary. And this is extremely powerful because it holds for arbitrary observers. Like these could run algorithms that run for a doubly exponentially long time. It just means whatever we do, they cannot tell the difference because it's information theoretically protected. The other one is in a sense less powerful because an observer that has an extremely powerful computer could break it, but it holds for a polynomially large number of copies. So this is for the experts. Only if you're very mathematically inclined, this is a definition of a approximate unitary K-design, where these orderings are orderings in CP distance. Yeah. Okay. Actually, I wanted to show you the theorem. I was sort of surprised by that slide. What we show is that an approximate unitary design can actually be generated in a depth that is logarithmic in the system size. So not only do you have something like after some polynomial time, which is already much lower than the depth you need to generate a uniformly random unitary, do you get something that is indistinguishable with a few copies. You can actually push this to log depth, essentially. So even after log depth, you get these very, very strong pseudorandomness properties. And if we have only 3 moments, all of these gates can be chosen to be Clifford unitaries as well. So I want to mention something because I think it sort of shows how surprising this is. If you have access to random permutations, some shallow circuit where each of these acts on bits, and every one of these gates is a permutation of bit strings, you know? This could map 0, 0 to 1, 1, 0, 1 to 1, 0, and so on, as long as it's like reversible. If you consider something like a reversible circuit that is shallow, and you apply it to 2 copies, 2 bit strings, one that is all 0 and one that is all 1, these bit strings will be exactly the same outside of the light cone of this one perturbed bit. I hope that makes sense, because these bits here only depend on things that happen here, and there the 2 bit strings are exactly the same. But now, if you are an observer and you want to tell the difference between a completely random permutation of all of the bit strings and something that is shallow, you can easily distinguish. A completely random permutation would just give you garbled nonsense strings, you know? 2 strings that both look completely random. But now I can apply it to 2 copies and see that they are the same outside of the light cone. And that should tell me that I not actually have a completely random unitary. So classically, if you only have access to reversible operations, the thing that I'm describing quantumly is simply impossible. And in fact, quantumly, the entire thing only works because locally, everything is so entangled with the rest that if you only take a look at something locally, everything looks maximally mixed anyways. And this sort of extra obfuscation that you get from quantum is sufficient to push the depth down to something that is logarithmic. So yeah, I hope it's sort of somewhat surprising to you that even though the light cone size is really small and doesn't reach even remotely the end of the line, you get something that is indistinguishable. All right, the second theorem that I want to show you is very similar, except we actually need to choose PRUs to get PRUs, which means pseudorandom unitaries. These are the things that are indistinguishable in any quantum experiment where the observer only has polynomial time resources, so you can't run algorithms forever. With a depth that's slightly more than logarithmic, we can't get away with logarithmic, unfortunately, because there's counterexamples. You get something that is indistinguishable under sort of standard cryptographic assumptions. So before I show you how we show this, I want to emphasize that these are essentially optimal. So in fact, in our paper, we can already show that just to get the approximate 2 design property, you require log n depth. And the bound works via something that I think many here might be familiar with, which is the anti-concentration property of random quantum circuits, something that shows up a lot in quantum supremacy experiments. And this quantity we can show simply cannot scale the way it should scale for a unitary 2 design unless you have at least log n sized light cones, because otherwise you run into counterexamples. And for PRUs, we are lucky because very smart people figured out how to learn shallow quantum circuits in 1D. And something that I haven't told you about random unitaries or uniformly random unitaries is that it's impossible to learn them, right? I told you there's doubly exponentially many of them. So clearly every fixed random unitary is only specified by an exponentially large number of bits. So any learning algorithm would have to specify an exponentially large number of bits, and clearly this cannot run efficiently. So if something is learnable, it has to be distinguishable from uniformly random, because otherwise there could not be a learning algorithm. So just the fact that this learning algorithm exists in at most log depth by these very smart people shows us that our result is basically optimal. And it's based on the fact that if we have something that behaves like this theorem, basically saying if we have 2 patches, you know, these strings here are qubits, and I'm applying a k design here, and I'm applying a k design here, and they overlap on some number of qubits that scales like the log of k over epsilon, where epsilon is like the error that I allow, you know, the maximum distinguishability of these unitaries from uniform. If I have a result like this, then I hope it's easy to see that we can use this to glue things together locally to get a globally indistinguishable unitary from sufficiently large blocks. So this is exactly what we do. If we have this sort of gluing result, you know, we just multiply 2 k designs that overlap sufficiently, and it's basically also a k design up to a slightly larger error on the entire space. Then if we have sort of sufficiently large blocks that will be log sized, we can use that these 2 together form a big random unitary, and then these 2 together form a random unitary, and so on and so on. And this sort of spreads a little bit like a, you know, like a disease, I want to say. And in 2D, I feel like it looks even creepier a little bit. I have very positive feelings towards this theorem. I don't know why I chose this example. But this is basically what happens. Eventually, we end up with something where the error is fairly controlled, and on the entire, like on all of the qubits, we have a globally pseudorandom unitary, or a k design in this case. So in fact, if we go to, if we look at random k designs, what we get is we have like log-sized blocks like this. And now we could, in principle, just compile these blocks into smaller circuits. And it turns out that polynomial constructions already existed. In fact, in every single one of these blocks, I can just run a polynomial depth circuit that converges to a k design. But polynomial on log n many qubits is log, right? In fact, it's not just polynomial, it's actually linear, so it's log. Otherwise, polynomial and log would be polylog, but yeah, I hope you catch this, okay. So in actually linear depth in n, you can generate these k designs, and this already existed. So now we only need to compile these blocks with these linear depth k designs, but clearly linear and log is log, so everything works out fine. I should say I'm citing sort of a recent paper that gets the k dependence up to almost optimal, but it has been a long line of works that eventually led to this result, and I should have cited at least Brandao, Harrow, Horodetsky, I'm just realizing, who were the first to prove the polynomial dependency. But at least I said it. Okay, so for the PRU part, we do something extremely similar, except that now in the blocks, we don't run just random quantum circuits with IID gates, where we have already some bounds on how fast this converges to a K design. Instead, we use some very recent results uh, something called the PFC construction, based on a work by Medgar, Poremba, Sina, and Ewan, that just multiplies together like a random reversible function, like a permutation of bit strings, then a random phase function, and then a random Clifford unitary. Random Clifford unitary you can build with polynomial depth circuits anyways, and the random permutation and the random function you can initiate with a pseudorandom classical function. And you know, there's all this cryptography that basically says terrible things happen if these, at least to cryptography, if these one-way functions don't exist. So we strongly believe that they do exist, and based on these assumptions, just plugging this into PFCs, oh, this is not what I wanted, gives us something that is completely indistinguishable on the blocks. And we already know if something is indistinguishable on the blocks, we can glue it together to something that is indistinguishable on the entire thing. So our contribution is really just the gluing part. And the thing that we use to build the blocks, this already existed. And yeah, it was based on a construction from this paper. And then Huang and Ma proved that this is actually a pseudorandom unitary. So, okay, I also want to show you very briefly how to prove the gluing lemma, and this is maybe a little bit more mathy. But basically what we're using is, if you have these completely uniform random unitaries, then there's very nice formulas, as I told you before, to compute the expectation values. And the way you do this is, if, for example, you have some high moment, it's like many tensor copies applied to some matrix A, which let's say we denote by phi h, h for har, then you can always expand whatever this is into permutations of the k copies. Think of the copies as like, you know, wires, and the permutations are literally just permutations of the wires. And on every wire we have some d-dimensional space, for example. So it turns out that you can always get this very nice expansion, and we also have fairly good understanding of these coefficients that you get. So I want to do something that I feel like is maybe a little bit risky. The first thing I want to explain is that it turns out that in the Hilbert-Schmidt distance, or in our product, these matrices become approximately orthogonal. And it also turns out that this thing in the Hilbert-Schmidt product is basically an orthogonal projector. And you would really like to just write this as the sum of the rank 1 projectors onto the permutations, but you cannot because they are not orthogonal. But they are approximately orthogonal. So basically what we can do is we can still write this as the sum of the rank 1 projectors and then show that we only incur a very small error doing this. Okay, once... Yes. WG just stands for Weingarten. Sorry, Weingarten function. It's just a function of the permutations and of the dimension that we act on. So zeta here, let's say, is the size of the block. So that's the dimension. And this is clearly a permutation if you multiply two permutations together. And basically, they are more or less defined as the coefficients in this expansion. So let's say there are some numbers such that this holds. And these numbers have a nice property, namely that basically they are sort of they fall off very fast off the diagonal. So this matrix sort of somewhat orthogonal. So once we have this, and let's say you just believe me that these things are approximately orthogonal, so we can ignore many of the off-diagonal terms, then we can do something really cool. And I hope it's okay that I just write this as a sort of a vectorization. You know, you can think of a matrix as a vector of n squared many entries. I hope that's okay. That's all I'm doing here. And once you do this, I can look at what happens if I multiply two or concatenate two of these Haar random channels together in the way that we do it in the gluing lemma. And now the funky thing that happens is these permutations, they factorize in the qubits. So we can do this, and then we multiply these two permutations. But if two things are like approximately orthogonal, basically we can ignore up to a small error all of the terms where these are not the same. This is where the inner product of these comes into play. You know, if I multiply these two blocks, I end up with the inner products of pi and sigma and the Hilbert-Schmidt inner product, and this will be strongly suppressed because they are approximately orthogonal. So in a sense, up to some error, you have to be careful if you do all of this. There's some more details, but eventually you end up with something that looks like this, and then basically, okay, I mean, these are two projectors onto these permutations. So basically, we just use that the permutations factorize on the qubits again, and we have the sum over all of the permutations, which we assumed is basically the same as taking a Haar random average over the entire thing. So the entire proof just boils down to figuring out how big are the errors while doing these in the norm that is interesting in this setting. And I want to say, this proof is sort of clearly a caricature of what's actually happening, and our original proof was quite long and used a lot of representation theory, but we sort of ended up with a 2-page proof. So I invite you to read it. I actually think it's sort of digestible in an afternoon session or something like this. So yeah, we're very proud of the 2-page proof. So okay, let me give you some applications. I just want to see if I'm in time. Okay, I have to hurry a little bit. There's a couple of applications. One of them, for example, is we can either we can apply a PRU to, let's say, some system where we hide a long-range interaction, or where we do not have any long-range interactions. And in both cases, if we apply a PRU, the two systems will be essentially indistinguishable. But if I have access to the inverse of the unitary, I can reverse and see long-range interactions, because if I have access to the inverse, I can see light cones. I hope that's sort of clear. If I have access to the inverse, I can do a perturbation at some point, but everything outside of the light cone will cancel out if I have a shallow circuit. And if I apply this to the setting where I hide a long-range interaction, it shows that some of these experiments where you can sort of black box reverse the direction of the time might have an advantage over experiments where you do not have this feature. And that provably, because in these experiments you can do something that can provably not be done in, without the reversal of time. Very similarly, you can, for example, apply a PRU to either a product state that is topologically trivially ordered, or to the toric code, and you have only increased the depth by something like polylog at most, and some definitions of topological order are basically based on the equivalence of polylog circuits. And for these definitions of topological order, we can show that it is computationally hard to show the difference between a state that is topologically ordered and one that is not, just based on measurements. Yes?
Sorry, what was the assumption for the PRUs?
It's that LWE cannot be solved in sub-exponential time.
LW hardness, okay.
Yeah, but we need sub-exponential.
Well, that's better. Okay.
We actually need sub-exponential hardness, yeah. Because on the blocks, everything becomes logarithmic, so sub-exponential very quickly becomes polynomial, unfortunately. But yeah, so we need some strong crypto assumption that is still somewhat standard, I would say. Yeah. So the last application that I want to show you is actually a learning-based one. And it's based on a paper by Huang, Kung, and Preskill, where they showed that if you have the access to applying a 3D design, basically, to states, then you can use measurements in the randomized 3D design basis to learn many properties, or to predict many expectation values of measurements in this state without actually doing the measurements. So you only do a couple of snapshots, and this allows you probabilistically to estimate m observables with only log m many samples. And we can basically show that the same thing can be done with log n circuits, and I feel like many of you will be aware of classical shadows. That's sort of a really big deal. And so in experiments that want to implement this, I would argue that most experimentalists already just do this. You know, if you talk to an experimentalist and tell them to implement a Clifford unitary, they will tell you they can do like 3 gates. I'm exaggerating a little, but essentially no one will just do all the super deep Clifford circuits in an experiment with a very high fidelity that significantly reduces the number of qubits that you can do interesting experiments on. So I feel like we're sort of justifying what many experimentalists were already doing to some degree.
So is this the scheme with the global unitaries, where they do this random global part separate unitaries?
Yes, so there's two settings. Sorry, I should have, I feel like I'm, yeah.
I want to make you go over time.
No, that's my fault,
that's
clearly. But yeah, the setting is you apply a random Clifford unitary, a globally random Clifford unitary to a state. Then you do measurements in the computational basis, or I should say then in the stabilizer basis that you have generated. And from these, you can then build something that's called a classical shadow, and this classical data allows you to predict other observables.
So you can do this in the circuit now is logged out.
We can literally do the exact same thing. And basically we do the same thing, but in the proof, like the inversion step that you apply classically, we just apply still the completely random measurement channel, and that incurs some error. That actually scales like the 1 norm and not like the 2 norm as in the original paper, which doesn't matter for some of the main applications like fidelity estimations, where the rank is 1 anyways, but there could be some examples where, you know, you get the exactly wrong scaling of the coefficients of the, you know, of the eigenvalues of the density matrix, where this blows up, but the original paper doesn't. But I feel like most applications where you actually care about these global unitaries have small rank anyways, and if they don't have small rank, then the 2 norm is also large, so we are not that worried about this. Okay, let me give you 3 little updates. One is people worked really hard to use more and more structure to get better constructions. Some people figured out how to do log depth with inverses. This is not 1D architecture anymore. This is basically, you have all-to-all interaction log depth, but this can actually be done. This was by Laura Cui, Tommy Schuster-Brandau, and Huang. Then people also figured out how to do it in constant time even, if you have access to the parity function, which is a non-local gate. But if you have this non-local gate, you can even do constant depth. And also, what is it? Yeah, if you have access to ancillas, something that I haven't told you so far, you can even do designs in log depth. So that's kind of crazy. We already knew that this is true for k equals 3 because Cliffords can be sort of very nicely implemented with ancillas. But even for higher k, this can be done. It was done by this was done by Cui, Schuster, Brandau, and Huang, and the inverse optimal PRUs was done by Schuster, Ma, Lombardi, Brandau, and Huang. All right. Then something that we did, or that I was somewhat involved in, we figured out what's true for other groups. And some funky things start to happen. So it turns out that if you want relative error group designs, this basically only works for the unitary group if you look at some standard groups. Almost immediately you get linear lower bounds from the invariants that show up in the commutant of these other groups. So this is true for Clifford up after k larger than 4. For k smaller than 4, it's a unitary design, so clearly it has the same behavior. But so this we kind of knew fairly quickly, that you get all of these counterexamples from the representation theory of these groups. What kind of surprised us is that if you only look at additive error state designs, which are sufficient to show indistinguishability for states, everything sort of goes through again in log depth, except for the match gate group, which is M of n. That one just defies all of these attempts to make gluing work. And also anti-concentration is sort of a different tier altogether. All right, so the very last one is something that we are going to do. We have already figured out how to get approximate state designs in log depth for just standard unstructured random quantum circuits. You know, in our construction, we need to choose the blocks, and then we have this sort of almost artificial thing where we can't choose gates between the blocks. And if I want to have like a higher k, you know, as in k design, I need to choose a different circuit layout. It's slightly strange. And the previous 2 slides were about papers where we try to figure out what happens with these weirdly unstructured circuits, where we can pick the structure of the circuit to make the pseudorandomness as good as we can. This is about the other direction, where we try to go back to just standard random quantum circuits and figure out if just adding random gates in between the blocks might actually mess up the pseudo-randomness, which I guess nobody believes that this is true. Having some extra randomness in your circuit shouldn't help you distinguish. But in principle, it could be, and we are finding some first evidence that this is not the case by showing at least the two design property. All right, so I'm basically done. There's some open questions. A funky one is the optimal scaling maybe not log n times k, but log n plus k? We can't rule this out. But yeah, I would love to chat about this at some point.